I'm glad to see so many people survived it and made it here in one piece. Thank you very much for sticking it out all the way to the end of the conference. I'm going to do my best to go out with a bang. So let's recall the outline. Last time, yesterday, at this time, we spent a lot of time talking about some more geometric properties of sheaves. I really think that one of the undervalued ideas is the role that the LAPLACIAN plays in sheaf theory. Algebraic geometers know this inside and out. Hodge theory is so important to them, but the rest of the topological community, I think there's so many cool things that one can do. But to be honest, everything that I've talked about so far is really kind of simplistic, as is usually the case when you're talking about applications of mathematics. The simplest stuff is the most easily applied. It takes a lot of work to really find an honest application of more sophisticated ideas, but that, of course, is the goal, to keep pushing things ahead. What I want to talk about today is going to begin with the notion of moving beyond the vector space coefficients that we've been working with and to try and do something that's a little less linear algebraic. Of course, sheaves can take coefficients in any kind of category you want, but if you want to do things like cohomology, you really kind of want an abelian category. But more on that later. There have been plenty of examples in the recent past, and even a couple in the distant past, of people using sheaves in real applications where the coefficients are not in the category of vector spaces and linear transformations. A lot of examples out there just use sheaves or co-sheaves that are valued in set. There's a nice paper, I don't know when it came out, sometime in the past decade, by De Silva, Munch, and Patel that used sheaves of finite sets to describe Rabe graphs. Technically, these were co-sheaves, and they were constructible as opposed to cellular, but really the same idea. And they used some basic properties of co-sheaves in order to be able to say things about smoothings, approximations, stuff that made people in computer science pretty happy. Similarly, Abramsky at Oxford for a long time has been using sheaves of sets to talk about contextuality, paradox, some interesting logical things, having some implications in quantum stuff. All very cool. Most of these applications are using the structural properties of sheaves as opposed to the obstructive properties. There's not that much sheaf cohomology going on besides global sections, because the category of sets, there's just not a whole lot that you can do with that as far as cohomology. At this point in time, I've done a little bit of work with Sanjeevi Krishnan on applications of sheaves of semigroups. That sounds a lot more impressive than it is. This is really a very small step in that direction that had to do with a certain tracking problem where things are changing over time, and you really have to pay attention to the directedness of the time axis. In order to solve some problems, we found it convenient to work with sheaves with a positive cohomology that's valued not in vector spaces, but in cones, positive cones sitting inside of those vector spaces. That's a fun story, but it gets in the weeds really quickly. It's kind of technical. And for the impact, I think our time would be better served elsewhere. Something that is really, really exciting is some recent work by Amit Patel and Bob McPherson on trying to extend persistent homology to what Amit calls generalized persistence. This, instead of being valued in vector spaces where you need field coefficients in order to define persistence, It uses a Mobius inverse along with some other really cool techniques in order to get it to work in integer coefficients, really coefficients in any abelian category. And the secret sauce behind it all, besides the Mobius inverse, is sheaves, or rather the bi-sheaf that Patel and McPherson introduced. I very, very highly recommend taking a look at Amit's papers on this. If you have any interest in persistent homology, topological data, anything like that, there's some very, very high quality work here that touches on sheaves that are valued in more than just vector spaces. But what we're going to focus on today is a category of data for our sheaves that is a bit more general. This is not going to be an abelian category, so it's going to be difficult, if not impossible, to get cohomology to work easily in general, but we'll do what we can. This is a data category that goes beyond vector spaces that I think is very, very general and is really worth taking the time to talk about. This is based on work with Hans Ghrist, who's a PhD student at Penn in electrical and systems engineering. This is working with lattices, not the kinds of lattices that physicists talk about, the kinds of lattices that mathematicians work with. Let me give a little bit of background, just because this is a big subject that often doesn't appear in background education. What do I mean by a lattice? What I mean by a lattice is a partially ordered set with a pair of operations that satisfy a bunch of properties. By partially ordered set, I mean that I'm going to draw these elements as nodes, as vertices in a graph, and I'm going to direct everything vertically. So there's a notion of order, but it's not a total order. It's partial order. Some things are not easily compared. If I take two elements in this lattice, I can talk about its join that I use this kind of symbol for. This is a generalization of a least upper bound or a union or a maximum. Likewise, I can talk about the meet, which is the dual notion. This is like a greatest lower bound or an intersection or a min. The notation would seem to indicate that there's a logical component to this. Indeed, there is. You can represent Boolean algebras as particular types of lattices in which join and meet becomes or and respectively. Now you can define all the properties for these things. You can define lattices algebraically. You can define them in terms of categories. There are lots of different ways to get at it. I'm mostly just going to draw a whole bunch of pictures and give you some simple examples that we're going to refer back to later on today. Simplest example of a lattice is take a finite set and then look at the power set lattice of X. If I look at all possible subsets, then I can order those subsets in terms of inclusion. That is, of course, not a total order. It's just a partial order, but this gives us a notion of a lattice because I can interpret the join and the meet as literally union and intersection. Another simple example of a lattice is the partition lattice of a set X, where what I can do is I can take that set and think of it as one collection, or I can break it up into sub-collections. In data science, you would call this clustering. And all of the different ways of clustering this set, of partitioning this set, can be arranged in terms of how coarse at the top or how fine at the bottom the partitions are. Now, there's another class of examples that are really not well known, but these are very cool and I think very, very useful. It's not a new idea. This is an old idea. It goes back decades, but it hasn't really got a lot of play in the mathematics world, and it ought to. This is something called a concept lattice or a Galois lattice, depending on whether you're German or French. The idea is the following. Start off with a binary relation on two sets. So I'm going to take two sets, and I'm going to think of a binary relation, something like a binary matrix of zeros and ones. One often calls these two sets the objects and the attributes. So think of one of the sets as being people, and the other set as being attributes that these people might share. Maybe this is a database that is keeping track of different information about different customers for your company, something like that. Okay, now this binary relation is something like a kernel for a transform. What do I mean by that? Let's pick an attribute. Let's say, there's this one thing. I want to know which of my customers has that attribute. Say lives in the UK. And so I go to the database and I look at the customers who have that attribute. And then I do the inverse transform. And I say, okay, I look at that subset of customers. What attributes do they share? What attributes do all of those customers, all those agents have in common? And then I go back down to my original space. That's like an inverse transform with respect to this kernel. If you take that pair, those blocks of objects and attributes, that all the objects have all those attributes, this is sometimes called the intent and the extent of the concept, then that concept becomes an element in a lattice. You can order concepts based on inclusion at the level of attributes or inclusion at the level of objects. And that gives you upsets and downsets in what's called a concept lattice or a Galois lattice. This goes back decades. These are very interesting lattices. Let me do an example, because these things can be a little hard to visualize at first. Let's say we talk about various social media platforms like Twitter, Facebook, Insta, TikTok, et cetera, et cetera, et cetera. Those are going to be my objects. Let's look at some of the attributes that they might have. Maybe they're text-based. Maybe you can upload images. Maybe you can upload videos. Maybe the social network is directed. That is, I can follow you, but you don't have to follow me. Maybe it has upvotes. Maybe it has downvotes. Maybe it's based in the USA. Maybe not. Maybe there's a private mode. Maybe you can spread disinformation on this network. If I take what I know about those social networks and what I think is true about these different properties, I get a certain binary relation. If I build out all the concepts, look at all the collections of these social networks have these properties and order them, then what I get is the following Galois lattice. Looks something like this. It's got a global minimum and then a global maximum. The global minimum is all the social networks globbed together. The global maximum is all the properties globbed together. I've labeled the concepts with where the first entry shows up. This is a good way to interrogate the data structure. It's a good idea to examine upsets. That is, you pick a node and you look at everything that is above it. So for example, if I pick YouTube and I take its upset in the lattice, then what I can do is look at that and see, oh, TikTok is included in that. That means that any property that YouTube has, TikTok also has. I can see that some of those properties include it being a directed network, having a private mode, and like everyone, the ability to spread disinformation. You could also look at downsets. I could take all of those social networks that are USA based and look at the downset of that and see that that's really everybody except TikTok on this list. And then intersections of these, really interesting stuff. These are a very cool class of lattices. We're not going to do a whole lot with them this morning, but they're so interesting. I just wanted to get an example out there to raise consciousness, as it were. The idea is lattices are really nonlinear structures. I'm going from a total ordering from a linear structure to something that's very, very nonlinear. The problem with sheaves taking values in vector spaces is everything's got to be linear. I think that looking at sheaves of lattices is going to be a really good way to get at nonlinear information, nonlinear data. Why might we want to do that? Well, the past 2 days, we've been spending a lot of time looking at examples involving opinions or opinion dynamics or preferences. That's really difficult to model. There's a lot of internal psychology going on that, as a mathematician, I don't know much about. But if you look at how these things actually work, it's not so linear. Things vary from person to person. The funny sort of meme on the left that compares what different people mean when they say, oh, that's good, that can vary quite a bit depending on where you're coming from. From a less humorous point of view, using words that have some sort of probabilistic connotation to them is really kind of sloppy. When someone says that something is likely, there's a whole range of what that can mean depending on who is saying it. There's some notion of ordering going on, but it's much better represented with a structure that is not a total ordering. And in particular, individuals have these sort of internal structures for opinions, preferences, perceptions. I think that lattices might be a really good alternative to using vector spaces and scalar intensities to model things. For example, if I'm trying to decide whether something is true or false, it might not be just a binary, and it might not even be a probability, a totally ordered intensity. It might have a much more complicated structure. If I say that something is probable versus it's possible, I might not have a really rigorous ordering on those two. I might use those two interchangeably. But if I say that something is likely, then that's definitely stronger than both possible and probable. A lattice might be a good structure for these kinds of really difficult to model things. However, we have this problem of individuation. That is, I have my internal structure for what I think, how I grade different notions of truth versus falsehood. And you have your internal structure that I can't see. I don't know what your internal structure is. The only thing I know is what you tell me. And the only thing that you know is what I tell you. And the words that we wind up using in discourse might be very different than whatever sort of nebulous psychosyntactic structure is inside my head that I might not even understand myself. But the only medium is communication, is discourse. When I say, sure, sure, that might mean a very different thing than if you say, sure, sure. We might interpret that differently. So you could motivate something like a sheaf of lattices by saying that I've got my internal nonlinear structure. I give expression to that in some common language, and I hear you talking using a common language, and I pull back. I perceive what you're saying. You do the same thing with your perception, with your expression, and the entire system has to talk, has to reason, has to do some sort of computation to figure out what is true versus what is false, and to what degree do we think that this is so. Now, again, I realize it's kind of dangerous for mathematicians to tread into the social sciences in general, but if we just take this as a motivation for, hey, let's start thinking about sheaves of lattices, then being very careful before we draw any conclusions about how society operates, how politics works, then we're safe. And I think we get to some really cool math. Here's another example where I think a sheaf of lattices might be helpful. Let's say we're trying to do politics. We're trying to build a coalition. So I've got some network of people, and there's people I know, but there's a much larger group that needs to come to consensus. Let's say there's a vote, and we're trying to figure out who's going to vote in favor, who's going to vote against. Consider a sheaf whose stalks correspond to the power sets of the neighbors. So what I'm going to do is I'm going to, for myself, look at all my neighbors, including me, and build the power set lattice of that. And an element of that is the people who I think are going to vote in favor, the people who are going to join the coalition. And then everyone else is not going to join the coalition. If I'm talking to you and I know my people and who might be on board, and you know your people and who might be on board, and we know some people in common, we can compare what we think in terms of the people we know in common and then try to come to some sort of consensus. So maybe the vertex stalks are private estimates of who's going to support the vote. And then the maps to the edge stalks are expressions. Oh, I think this person's going to be on board. To represent this in pictures, right? Here's me, and here's the people that I know, and I have estimates of who's going to go along with it. There's you have people that you know, and then when we talk, we can register our estimates in terms of, do we agree on the people that we know in common? That is one way that you could try to set up a sheaf of lattices of power sets in order to solve an interesting problem. But how do you go about doing that? How do you go about solving that kind of problem? And how do you do things that are more subtle than just yes or no, for or against? Well, we need to talk about how we communicate over a lattice. It's not as simple as a linear transformation with a vector space. This is a bit subtle. It helps if you're good with category theory, but I'm just going to give a very sort of straightforward, simple description of the proper type of morphism. These are called Galois connections between lattices, and they come in pairs. So if you have two lattices, X and Y, a Galois connection is actually an adjoint pair of morphisms, of maps that take elements to elements and preserve the partial order. In order to be that adjoint pair, you have to satisfy the following condition, that when you map forward in X and you're less than Y, that's the same thing as X being less than the inverse map of Y. If you do the category theory, that this is literally a set of adjoints, and using what we know about how adjoints work, you can actually write down formulae for how to compute this. The inverse or the dual given the forward mapping, and vice versa. Okay, so we've got these mappings that allow you to go both forward and back, and that's really good news for being able to do things like communication, where you're passing messages back and forth. What is it that we might want to do with sheaves of lattices? Well, for all of the examples that I've talked about so far, what we'd really like to be able to do is find global sections, is do local communications and then have a global system come to some sort of consensus. But we can't just compute the zero-dimensional cohomology. We can't just do what we did yesterday and run the heat equation on this system, because I don't know how to do differential equations on these lattices. I don't know how to set up a heat equation. What's the LAPLACIAN? But it does sort of point us in the right direction for what to do. If we had a LAPLACIAN or something that morally acted like a LAPLACIAN, we might be able to do something. Here is a proposed definition for what the LAPLACIAN should be. Hans Ries and I call this the Tarski LAPLACIAN. Let's start off simple. Let's say our base space is just a graph, vertices, edges, and it's a sheaf of lattices. So each vertex, each edge has a lattice, and they're all connected with these adjoint pairs of Galois connections. If I take a zero cochain, X, that is a choice of lattice element for each vertex stalk. These could be like everyone's internal representation for what they think of the system, true, false, whatever. Then the LAPLACIAN acts on that zero cochain as follows. Here's the formula. It's kind of complicated. It looks weird. There's a whole bunch of meets that's kind of like taking a whole bunch of intersections. And there's some sheaf mappings from a vertex to an incident edge that goes forward. And then there's some reverse mappings. That's the thing with the lower dot that goes from data over the edges back to me, back to that vertex. And what it's doing is it's pulling information from my neighbor's vertex data, mediating it through discussion over the edge, and then pulling back to me. Now, the formula looks a little bit complicated. Why is this a LAPLACIAN? Does it act like a LAPLACIAN? Does it look like a LAPLACIAN? It doesn't really look like a LAPLACIAN at first. But if we take that formula and do a little bit of expansion using some of the distributive properties of how these things work, we can isolate out the terms that are really local to me, the vertex at which I'm applying the LAPLACIAN, and then those terms that involve all of my neighbors. And what I can do is split that up into two big meets that, again, are intersected. And this, I think, really does make it look like a classic LAPLACIAN. What do I mean by that? If you go back to the definition of the graph LAPLACIAN, there are two ways to represent it. You can represent it in terms of the sort of Hodge definition using the boundary matrix and its transpose, or you can represent it in terms of the degree matrix, this diagonal matrix, minus the adjacency matrix. That's exactly what we're seeing over here. The definition at the top is really in terms of you map out, you map back in, like a Hodge LAPLACIAN definition. This decomposition on the bottom is split in terms of things that are localized about me. That's like a diagonal matrix. And then all of the off-diagonal terms where I'm talking to my neighbors. That's like subtracting off the adjacency matrix. Where that meets in the middle is something like a subtraction. Okay, that's a little bit fanciful maybe, but I really do think that that is at least a first step towards arguing that this is an honest LAPLACIAN. The next step is to see whether it acts like a LAPLACIAN. Does it diffuse when you apply it? Does it work like a heat equation? Well, there's a classic theorem in lattice theory. It goes back to 1955 with some earlier antecedents, This is called the Tarski fixed point theorem. One of the really cool fixed point theorems that I think most topologists have never heard of. It's really cool. Let's say you've got a lattice X. Let's say it's a complete lattice, so it has all meets and joins. A finite lattice would do the trick. If you have a self-map, an order-preserving endomorphism of that lattice, you could talk about its fixed point set. It's just the things that go to itself. Yeah, right. Good. The fixed point set of a lattice morphism is a non-empty, complete quasi-sublattice of X. That means, thought of in and of itself, it's a lattice. It's not a sublattice of X because it doesn't necessarily have the terminal element at the top, right? It's a smaller thing. But as a subset, it is a lattice. That's the Tarski fixed point theorem. Really useful, very cool, not that hard to prove, very general because lattices are all over the place. Okay, now here is the sheaf theoretic version of the Tarski fixed point theorem. And it's the reason why we call this the Tarski LAPLACIAN. And I would call this the HODGE-TARSKI fixed point theorem. It says if you have a network sheaf of complete lattices, the global sections can be computed via this Tarski LAPLACIAN, just iterating it over and over, like a discrete time heat equation. Those global sections, what is morally the zero-dimensional cohomology of the sheaf, is the fixed point set of the identity transformation meted with the Tarski LAPLACIAN. So if I just apply that operator over and over and over again on my sheaf, no matter what my initial condition is, my initial zero cochain, I converge to a global section. And in fact, the fixed point set of this is exactly the set of global sections. Now, remember yesterday when we were talking about the heat equation, I made sure to include the discrete time version as well, even going so far as to derive that the operator, the evolution operator, is the identity minus the LAPLACIAN. That's exactly what we're seeing here in this Tarski fixed point theorem for sheaves. It's structurally the exact same thing. If you look at the fixed point set of that discrete time heat equation, that's exactly the global sections when we were talking about vector space coefficients. That's very cool. This is really a discretization of a heat equation, but for sheaves of lattices. And we get the very non-obvious corollary that the global sections of such a sheaf is non-empty, and it's a complete quasi-sublattice of the zero cochains. And plus, what's really cool is it's an algorithm. You just talk to your neighbors, do diffusion, and you get to a global section. Very nice, very nice. Now, there's a whole bunch of interesting questions here. The first question that I am sure everybody wants to ask is, how do you do this for higher dimensions? How do you do this for higher dimensional base spaces? How do you get higher dimensional cohomology out of this? Because, of course, when we were talking about vector spaces, that all worked in higher dimensions. The Hodge theorem works for cohomology in arbitrary dimension. You just look at the harmonic cochains. What can we do in this case? Well, I can think of the global sections as being morally zero-dimensional sheaf cohomology. Unfortunately, the category of lattices and lattice morphisms not an abelian category, so I can't do the straightforward thing of trying to define sheaf cohomology using kernels mod images. Those don't really exist. So what are we going to do? Well, let's try to do Hodge theory, even though we don't have classical cohomology. If I take that definition of the Tarski LAPLACIAN on a zero cochain for a sheaf of lattices over a network and say, well, what if I had a sheaf of lattices over a higher dimensional base space, higher dimensional complex? I've just got lattices over all the cells. I have Galois correspondences, lattice morphisms that connect everything up. Then I can certainly make sense of k-dimensional cochains. I can try to make sense of this LAPLACIAN. It's not hard at all. In the above definition, replace the vertices with K cells, replace the edges with the cofaces. Take the co-boundaries of those K cells and look at the stalks there, look at the sheaf maps, the Galois correspondences there. You get the same formula for the same Tarski LAPLACIAN in arbitrary dimensions. This bodes well. It's still, we're not going to get Hodge theorem that says that the kernel of this, the fixed point set of this with the identity, is equal to the sheaf cohomology, because we don't know what the sheaf cohomology is. So let's just get out a hammer and bang on it and define the Tarski cohomology for this sheaf in terms of the harmonic cochains with respect to this LAPLACIAN. If I take the LAPLACIAN on K cochains and I meet that operator with the identity, I have a discretized heat equation. If I look at the fixed point set, if I look at what that diffusion operator converges to, morally, that's like the Hodge theorem. That ought to be giving me the harmonic cochains, that ought to be giving me something isomorphic to cohomology. So let's just call it the Tarski cohomology. And of course, the theorem that we proved in grading 0 works in higher gradings as well. It's a non-empty complete quasi-sublattice of the K cochains. Cool. But what is it? What does it tell you? I don't know. That's a really good question. I mean, this isn't a cohomology theory at all. You don't have all of the components that you need to be a cohomology theory. I don't know how to do excision. I don't know how to do anything. The only thing that I know is that this might be a sensible definition. This is one of the many open threads that have not been pursued. Lots of good things here to do. But instead of going down that path and trying to figure out, oh, how do we do it? I want to push the envelope a little bit. I want to talk about some things that we can and might be able to do with lattices that goes beyond anything that I have talked about so far. I want to look ahead to the future a little bit. This is the appropriate thing to do at the end of the conference. We've talked about 3 different tools that together do some really cool things. We've talked about cellular sheaves, we talked about lattices today. Yesterday, we talked about LAPLACIANs. That's sort of the threefold setup of this mini course. And I want to put those together to talk about how we might do reasoning, how we might get sheaves and Laplacian evolution on sheaves in order to get systems to reason collectively about complex situations. I think there's a lot of additional structure that lattices are really, really good for. I've mentioned already that Boolean algebras are special cases of lattices. We can do propositional logic in this language. I'm going to hit on some other things very, very briefly, things like residuated lattices that allow for intensities. And when you start adding in the categorical perspective, I think there's a whole lot that one can do. Let me give one specific example and then one more nebulous example. The specific example is some joint work with Hans Ries on KRIPKE semantics for doing distributed reasoning. I'm not going to go into too many definitions about KRIPKE semantics. If you know a little bit about first order logic. You have propositions, you have things like and, or, you have the existential and the universal qualifiers. KRIPKE semantics introduces a few more operators. Operators that allow you to talk about things that must be true versus things that might be true, or things that should be true versus things that may be true. There are lots of different ways to interpret these KRIPKE operators. If we have a multimodal KRIPKE system, what's called a KRIPKE frame, then I have some set of states, S. Think of these as things that I want to decide whether they're true or not. And then the KRIPKE frame consists of binary relations on these. You can take this setup and turn it into a bunch of Galois connections on the power set of states. If you're trying to figure out the truth versus falsehood of all of these different states, and you use a little bit of the language of lattices and lattice morphisms, then what you get are existential and universal instantiations, where the connotation for all of these is, I know that this subset S is true, this subset of S is true, versus I think that this subset of S is true. And you could turn this into something like a semantic sheaf, where you've got a graph of people, let's say over a social network, they're talking to each other, and they're trying to determine which elements of S are true and which are not true. But they're reasoning in this KRIPKE semantic way, where they're saying, oh, I know that this is true versus I think this might be true. So the stalk over each vertex and edge is going to be the same. It's going to be the power set of S, but really the lattice power set of S, where these mappings that go back and forth, these different existential versus universal mappings, are individuated person by person. Now, if you use that type of sheaf, you use that setup, and you replay the story of the Tarski LAPLACIAN for lattices, then what you get is a pair of dual LAPLACIANs, one involving the meat, like the way that we defined it before, that involves applying the existential qualifier first and then the universal qualifier. But you can dualize everything and take things in the reverse order and take the join of that. If you use these two different LAPLACIANs, then what the HODGE-TARSKI theorem tells you is, if you talk to your neighbors and you say to your neighbor, well, you know, I think this is true. And then they tell you, oh, well, I think that this is true. And I know that these people think that this is true. You iterate this over and over, then you get these kinds of logical chains where he knows that she thinks that this is true. And by doing that iteratively, the HODGE-TARSKI theorem tells you that this will converge to a global section where everyone comes to consensus in terms of what everybody knows to be true and what everybody thinks may be true. And again, you get dual forms of this. That's one interesting example of trying to do reasoning with sheets of lattices. It's kind of a simplistic example in the sense that every stalk is the same. Everybody's talking about the same sort of thing. I think there's a lot of interesting work to be done if you start individuating that with personal spaces of things that you think may be true versus public things that you're discussing, much like the opinion dynamics that we were talking about yesterday. I want to point towards a little bit of work in progress with Page North. And again, Hans and another graduate student, Miguel Lopez. This is trying to move beyond reasoning in terms of what's true versus what's false, or more generally, what must be true versus what might be true, and trying to put in some degree of certainty where that degree might be interval valued, or it might be valued in something much more general. This is work in progress. We don't have anything up on the archive yet, but the rough outline of how it goes is something like this. We think in terms of a lattice of propositions and reasoning in terms of evidences and upsets. So if I take a piece of evidence, a thing that I know is true in my lattice, then I can go up from there and look at everything that that would imply if that were in fact true. But what we'd like to do is not have a rigid true-false dichotomy with a Boolean lattice, but rather something with a strength of implication. There's a long history of what is somewhat unfortunately called fuzzy lattice theory. I think it's kind of a ridiculous sort of name, but that's the name that was used. These are lattices where everything is valued in the interval from 0 to 1 instead of being Boolean. Residuated lattices is the technical term. There's a lot of interesting work on fuzzy lattice theory by Bilolovec and others that goes back decades. It's the kind of thing that I think it's worth reading. I think it's worth reading, and I think it's worth trying to extend. And for us, the new ingredient that we want to bring to this is a little bit of enriched category theory. Instead of just slapping an interval from 0 to 1 on top of the elements of the lattice and then trying to get things to work out, move backwards a little bit. Start from the foundations, get the category theory right, and then try to retell the story that we've been telling for 2 days now. If you think about a Boolean lattice as a category enriched in just the set 0, 1 that has all finite meets and joins, all the other properties that I need in order to be a lattice, if we think of that as being sort of trivially enriched in the Boolean category, then we can talk about fuzzy lattices, lattices where you have more sophisticated notions of truth as being a category that is similarly structured, but now enriched in some commutative ordered monoid. So for example, we could use the interval from 0 to 1, thinking of that as commutative ordered monoid, or we could use other things as well. And here's the cool thing. If you use what's known about enriched categories in order to define weighted limits and co-limits, that is, we get weighted meets and joins. This allows us to replay the story of working with the Tarski Laplacian, of being able to prove what happens when you iterate that over and over, but now in this residuated sense, or in this weighted sense, where we can have a degree of certainty associated to the different things that we're trying to implicate. I apologize for not having a lot of details on this, but this is something that is not ready to be posted quite yet. I merely want to point in the direction that there's a lot of work to be done. That's not the only open thread. There's a whole bunch of open directions, and well, I have a finite and increasingly small amount of bandwidth to be able to chase after some of these things. So please, if you're interested, consider some of the following questions. Of course, the obvious thing to do is to move to higher dimensions. I've been talking about really, really simple settings where everything in the base is one-dimensional, it's really important to get the math to work on higher dimensional complexes at the same time as you're working with interesting examples of applications to those higher dimensional base spaces. If it was totally obvious, I'd have done it already. It's not totally obvious how to get interesting examples, how to make all the math work. Lots to be done there. We should definitely move beyond the heat equation. That's just one way to spread information over a network. This is not necessarily how social networks evolve. This is not how information spreads. If you spend time on social media, you see that there are waves of information. You see that there is pattern formation, like the kind that you find in reaction diffusion equations. A whole bunch of interesting things to be done beyond just using a LAPLACIAN for diffusion. I've talked about pushing things to lattices today, but we should move beyond lattices, do all kinds of crazy stuff. My perspective is very much that a sheaf is something that you program, and then you run that program in order to solve problems. If that is the right word picture, then the coefficients that your sheaf takes values in is really the programming language that you use. And we all know that different programming languages have different capabilities. But we should go beyond sheaves. Sheaves are not necessarily the be-all and end-all. The way that global sections are determined just by the one skeleton is somewhat limiting and maybe limits applicability. We should look at things beyond sheaves. We should definitely be looking at stacks. We should look at things that are maybe beyond that as well. And we should go beyond math. There are so many things that we topologists have to say to people in machine learning, artificial intelligence, graph signal processing. It's stuff that they really need. They just don't know that they want it. We need to do a good job of explaining what it is that we know, what it is that we can do for them in a language that they can understand. Already, the sheaf LAPLACIAN has started making some inroads in the machine learning community. I haven't talked about that, but that's a really interesting story. I think there's much more that we as topologists have to offer that world, and it might actually help them a lot and make a difference in things. It's not easy to do, but I think it is worthwhile doing. And with that, I'm going to thank all the people who have made the work that I've been talking about possible. This is a list of some of the people who've come through my group at Penn over the past several years, the people who are currently there. Many of these people are responsible for so many of the results that I have been talking about. So I definitely want to thank them and all the people that I've worked with. I definitely want to thank the organizers for this conference for doing a great job. I guess, I don't know. I mean, I haven't been able to see anything else, but I'm assuming that they did a really good job.